Okay, no, it's really for me a great pleasure to be here with you, but also I have to say a little bit of a great challenge because I would like to share with you a bit of my eyes. So the eyes of an experimentalist. How do we see things and which are the type of quantity we look at. In any moment, I mean, please feel free because I'm not totally sure to be able to be clear since there will be a different kind of way of seeing things and I want to share mine with you. First of all, I would like to define few concepts that you will see during the talk. So the type of system that we in the experiment are looking for, and we realize actually, is kind of a collection of neutral atoms at very, very low temperature. The reality is that we are never at zero temperature, but the temperature is very low, and in most of the case, we do ignore the effect of temperature, although it is always there. The type of figure that you see, that you will see in many of my talk, is this type of figure here. So this is what it is, and now I just want to give you a sense. So we have all these atoms which are in the gas phase, almost at T equals 0. But of course, I mean, we need to trap the atom. It's always, we are never really in the thermodynamic limit. That means that we are never really discussing in a proper way phase transition, if you want, because we are never in the thermodynamic limit. And our system is not free. You need to impose something that confines the gas. Okay? And it's almost never a box. So we use laser light to create effectively an harmonic potential. Okay, the harmonic potential, the system is always three-dimensional. Okay, even in some of the figure, it look like that it's 1D because I'm just making, let's say, maybe the design more 1D. In reality, we are always in 3 dimension. So the trap that now, and don't speak about our result in the lattice, I just want to focus in the harmonic confined case. We call this a bulk gas because, I mean, to make it a difference to lattice frequency. And you can decide the value of this frequency. And what does it mean? And this will become important, that you can have trap of different geometry. You can have a trap which is spherical, in the case the 3 frequencies are completely clear, equal, or you can have, let's say, always 3-dimensional, like elongated trap, they look like a tube where atoms are in 3 dimensions, or trap that are like a pancake, okay? So just imagine, this is important. The case of having really a spherical trap is something that we will not touch here, but we will touch the case in which the trap is roughly elongated. We call it cigar-shaped. So you can call it prolate and oblate. And the other case is where the trap is more, let's say, pancake-like, but it's never 2D. That's never 1D. This is never 2D. It's just there is elongation in different direction, okay? So and now these little dots are all my atoms, typically it's 10 to the 5. And what is very interesting is that we have a way to really control the two-body interaction. And so I would say that the main type of interaction were under the control of experimentalists was what we call, yes. Anharmonic correction are not relevant, and in case you do a bad job as an experimentalist, you see immediately the anharmonicity and you can compensate. For everything, it's interesting, beside the fact that in an harmonic trap, so the level are quantized, so if it's completely harmonic, the distance in energy is always the same. Our condensate, which is almost 0 temperature here, doesn't feel eventual anharmonicity that come to very high harmonic level. Okay, so the type of interaction is the one that we also heard a lot of type here. So it's which was dominating the field for almost 15 years. So we call it, nowadays we call it contact interaction. As you see, is basically a delta function. You really need to have the atom very close by to have the interaction effective. And it's depending by a single parameter that in the experiment we can change. The scattering length A, let's say, that give you the size of the cross-section in a collision, if you want to see this from the point of view of a scattering problem, you can control experimentally. I can make it 0, I can make it very, very large positive, very, very large negative. I have a tunability. That's why we call this tunable quantum gas. Of course, there is no angle dependence. It's totally directional independent, this interaction, so it's isotropic. And many, many things have been studied with this type of interaction. As you also know, it's very interesting and is highly non-trivial, a Bose gas with this type of contact interaction. But actually, very recently, the field have made a step forward. And the step forward was, I don't know. So the step forward was entering what we call jargonically in our field, lanthanide era. What do I mean? I mean that actually in the periodic table, there are many atoms. There are some atomic species which are extremely magnetic, okay, are the one responsible for the vibration on your mobile phone, are the strongest magnet. And those family is the family of lanthanide. And in particularly, the most magnetic atom is dysprosium, and the other one extremely magnetic is the erbium. So a few years ago, my group was the first one to bring in the quantum regime erbium. And then again, together with the other group, which was in Stanford, so my colleague Benjamin Leff was bringing to ultra-cold regime, Bose-Einstein condensation, dysprosium. So finally, it was possible to have a collection of ultra-cold in the quantum regime identical boson, which do interact also because of magnetic interaction. And this now it's becoming the field of strongly magnetic atom. The field of strongly magnetic atom is nowadays becoming one of the main direction of the whole field worldwide. Okay, so the number of experiments nowadays on lanthanide and in particular in erbium and dysprosium is really exponentially increasing. So why? I can tell you because this atom is easy experimentally to Bose condense. I think we have found a very robust way, but they bring together a lot of novel properties for many bodies, strongly correlated quantum systems. So not tough to do, but a lot of new properties, really the key that made this system so successful. And so you get in a situation in which a very interesting one, because now you are a dipolar quantum gas in which you have two totally independent sources of interaction, contact and magnetic, that can, counteract each other, and you can control who is winning. Or you can even put it, both of them, in the same way. But those are very different type of interaction. And so the feeling that really we had at the beginning, few years ago, was to be in an escape room. So that we really were observing in the lab things that we could not understand. And we also even gave explanation that were not maybe 100% correct retrospectively. And so the feeling was really to have to hunt for the key that will allow us to solve the puzzle that we will solve. I will try to give you a few examples of things that were really puzzling us and how then all the pieces were coming together. So let's have a look again to the interaction. That's the contact we already described. And the magnetic interaction is a type of interaction which is a dipole-dipole interaction. The dipole is magnetic. And you can imagine this to really have like classical magnet. You have two classical magnets. You feel the interaction even before they touch. So the atoms do see each other also before being in contact. And also, as you know, in magnet, you can have repulsion and attraction, pole north, pole south. There is a directionality that it's embedded in this angle. What does it mean? I told already you that the scattering length in contact interaction we can change, but let's fix it repulsive, so bigger than 0, so that the system is always stable in the sense of only contact interaction. But this one is more tricky, because this is an interaction that is attractive and repulsive at the same time, okay? How can it be at the same time? Yeah, you want? Yes, the magnetic properties is a permanent properties of an atom, because it's only related to the quantum number of the level of the atom. So the Mj, the J, the L, S, J, F, though these and the magnetic moment is only a collection of this quantum number. So it's really permanent. Even without magnetic field or without any quantization axis, you will have that the atoms are magnetic, and they can do very interesting, a new form of matter which have nematic properties, but I'm not studying this now. What I would like to tell you is that if you have two atoms, so what is key to understand before going on is the following. We are doing a physics in which we always have a magnetic field applied. And let's say that the magnetic field is in this direction, pointing up. Every magnet is aligning with the magnetic field, okay? That's by definition. So one atom, one single atom, would align with the magnetic field. So the magnetic moment is parallel. Now I have a trap which is three-dimensional. That means that I can have an atom here, here, here. All my collection of atoms are three-dimensional. They are everywhere. But now in this many-body system, I have all the atoms aligned with respect to the magnetic field. But, and this is the key point, there are part of them that will experience a repulsive dipole-dipole interaction because side by side is repulsive, but the same atom might experience attraction with one that is head to tail at the same time. Okay? So this one, this atom here will also experience attraction to this one. So you have an interaction which is at the same time attractive and repulsive for an ensemble of many atoms. So the question of answering is this attractive or not is already not a trivial question. You had a lot of talk about stability of N bosons. And one of the idea of stability is also that you need repulsive interaction. With the attractive, everything collapses. Here, you cannot say. Okay? But there are a few additional things to have in mind. And these if you look at this equation here for the dipole-dipole interaction, you would immediately recognize in the Lagrange polynomial that there is a pattern of this interaction, which is a D-wave pattern. So this interaction is a type of D-wave pattern interaction. So if the atoms are here, there is attraction. If the atoms are here, this is repulsion. There is a magic angle in which the interaction is zero. Okay? So in which way we can make the dipolar interaction more attractive or more repulsive? Well, here my trap enters to play. Because if I have this type of configuration, in average, my three-dimensional atom will be in average more likely to be side by side. Because it's elongated. I have more side by side than head to tail. If I have it here, it will be the contrary. Let's say now I have to maybe do it like this here. I will have the contrary. Okay? So in a way, you can change. So what I want to say is that the trap geometry combined with the polarization of the magnetic field allows you to, let's say, it's like an integration volume, which is not spherical. So you can make it this quantity more attractive and more repulsive. The type of energy functional that you have is the one that we discussed many times. In general, we use the Gross-Pitayevsky equation in which you have the kinetic energy. The trap, I told you, play a very important role. Then you have the contact interaction in the mean field approximation, and you have the dipole-dipole interaction in the mean field approximation. That's the typical things we use to describe. And actually, this Gross-Pitayevsky, if you, let's say, solve it numerically, describe very well, in many, many cases, the physics, but not in all the cases. So, and what I want to... Yes. And so basically that's just simply the energy functional is coming from the Gross-Pitayevsky equation with dipole-dipole interaction. So, and now the first question that one would like to answer is what happens in terms of the stability of the system. Will this collapse or not? Is it stable or unstable? Well, I mean, if you now enter in the situation in which you put the dipole-dipole interaction to be, let's say, attractive, mainly attractive, and the other one mainly repulsive, even if these two contributions have, I mean, in absolute value the same weight, the attraction will always win, because there will always be an advantage to favor attraction, because attraction is decreasing energy, so the system will, and the interaction is non-linear, so the system will always tend to make it the density higher in order to make attraction more strong. And this is always true in nonlinear interaction, okay? So if you have these two sources of nonlinear density dependent, there is always attraction that win. And so this was observed in chromium, which is an atom with a little bit of magnetic moment. And what was observed is that in this situation, you get a collapse, an instability, a phononic instability of the system that the author called the D-wave collapse, just to remember the D-wave geometry of the interaction. And what you see is that this is the typical image of an atom, of a cloud of atom. The color, which are, let's say, red, a very intense color, means high density. You have to imagine that you have like a Gaussian profile and you are integrating. So you have something very dense at the center and then the density decreases. And so in a less than a 0.3 microsecond, that for us is extremely fast, you see that the atom, so that the system are losing atom and getting in this type of collapse. And this is also true, I mean, in general, if you have a protostar with attractive interaction, as you know, this protostar will, for example, immediately collapse. No? And then getting very, very high density, so the collapse, so they want to decrease the energy, and so this is done by increasing the density, and then at some point the density is so large that everything explodes. Okay, so this was the understanding before using this lanthanide atom. But actually what happens later in 2050, a big surprise, because now we were thinking, okay, let's repeat the collapse experiment. Now that we have even larger magnetic moment, even larger attraction, the collapse will be even faster. And instead we saw that the system were changing the shape, but being stable. And also what we saw, this was in a geometry of the trap. Now here the blue is the illustration of the trap, which is the pancake type of trap here. But if you do the same experiment in a kind of cigar elongated trap in this direction, and in particular these experiments are done in this type of trap with the magnetic field in this direction. So this is the type of things you have to imagine. Okay, so there is a lot of attraction here. You see that there are a lot more likely to be attractive. And what we saw is that a normal Bose-Einstein condenser were initially increased the density. And then at some point when the density became roughly 1 order of magnitude bigger, larger than a condensate, it was stopping the density. It was stable, but very high density, stable, and the density was not further increasing. So we enter apparently in a new type of ground state with much, much higher density than what you would predict via the Gross-Pitayevsky equation. And that actually really was a big surprise. We didn't know what was going on in the community. Now we know, because everything was stable. So under dominant attraction, the system was not collapsing. So it seems that something was missing in all our understanding of the problem. And actually, if you would take the Gross-Pitayevsky equation and do numerical simulation of the ground state, you would always see instability. So the usual Gross-Pitayevsky that was very well working in all ultra-cold experiment was failing to demonstrate and show this stability. So there was something that were missing. After, let's say, a very intense debate in the community and me doing experiment and Stuttgart other experiment, and we were trying to understand, we took older paper. So we started to understand more and more, we and the community, that actually if you take the energy functional and you add an additional term that it's growing in density faster than the mean field contribution, then this term could actually act as a density regulator. So what does it mean is that while the mean field interaction will push the system to increase the density, at some point this term can pop in and regulate and tell you, no, I had some repulsion, which is density dependent. And there was a long discussion of what would be the physical meaning, the physical origin of this additional higher order in density term. And so the first proposal were proposing that this is a mean field two-body action. Maybe this is a mean field three-body force. And so there was a lot of discussion really considering that this gamma to be one, so three-body forces. And there's some paper. However, it was not really fitting with our experimental data. So somehow there was not, seems that, let's say, by considering a pure three-body force, that was not okay. And rapidly it was understood that really the reason are the Li-1-Yang term, that typically we neglect in our experiment, because typically this coefficient is very small, the density is small, so we typically neglect Li-1-Yang. But actually, in our situation, the Li-1-Yang term was extremely important because, first of all, there were some papers of many years before our experiment that were, let's say, developing the Li-1-Yang term also in presence of the dipole-dipole interaction. And this epsilon dd that you see here is the ratio between the scattering length and the dipolar length, so the ratio of the characteristic length scale of the two interactions. So this is a kind of this alpha parameter that you have here, and then this density dependence, which means that gamma is 1 alpha. And now we calculated spectrum of excitation, we excited in the experiment with benchmarked experiment and theory, and actually also we developed, which I don't have time to explain here, an interferometric, a very precise method to measure the Li-1-Yang. And everything was fitting pretty well. Pretty well, I don't want to tell you, not completely well, but pretty well, let's say. And it seems that really this new state of matter was then a Li-1-Yang fluid, quantum fluid. We started to use this word. The macro droplet, so this high density really droplet, was due to the Li-1-Yang. Another very interesting aspect is that once we enter in the let's say in this droplet phase, in this macro droplet phase, and then we switch off the trap, so the system is not externally trapped anymore, so the system will feel gravity, so our cloud of atoms will go down, but normally, since it's not trapped, it will also expand, will expand and go down. In this case, where really the gas were expanding like a little drop of water without becoming big. So it was self-bound by the Li-1-Yang interaction. Why in chromium was not observed this type of phenomena is because the interaction the dipolar interaction was too low with respect to our system. So before entering in this Li-1-Yang regime, they were suffering by very strong three-body losses. So they were losing inelastically the atom before the Li-1-Yang was popping up. Because of course in all these we are forgetting inelastic losses. But if the density becomes too big, the atoms are close, there is three-body losses that make that two atoms bind in a molecule and one remain atom, but then these release a lot of binding energy and they are lost from the trap. Two bodies are energetically forbidden because we are in the lowest atomic energy level. But three bodies in which two atoms convert in molecule and the other stay, yes. And for chromium, this was killing them before any Li-Yang, let's say, physics were popping in. Okay. Yes? Yes. There is a contribution via this function f. I think that also probably the prefactor is a little bit different in the, I don't remember, but for sure there is the contribution by this function that's a complex function of the dipole-dipole interaction. But this is not that this function is increasing a lot the prefactor. Is increasing a bit, is by itself bigger, but really the main physics is that the density, since the density is increasing so much, then at some point it pops in. So this, well, the scattering length can be, let's say, something like around 100 atomic unit, and the density is, you have to calculate, but the density is maybe 10 to the 14 centimeter cube per centimeter cube in a macro droplet. In a BC is 10 to the 13 or few 10 to the 12. Yeah. Sorry, what's the, yes? Let's say in time, you mean, let's say, yeah, exactly. In a long time scale, the three-body loss will depopulate the Bose-Einstein condensate. But you can, what is this? You can see, so let's say if you do this experiment, so you can find the sweet spot. So you can find, now I cannot go too much into atomic physics detail because we will get lost, but you can find situation in which the three-body losses don't play any role, and our state, the one, and that's how we do, our state have an extremely long-lived, or you can get in situation of tuning of interaction when the three-body is really very important and the system is maybe dying after 10 milliseconds. You can tune this. Typically a normal BC has a lifetime in the trap that it's about 10 seconds. And I will show you a new phase of matter, which is the supersolid. We have the same lifetime of a normal BC. We can create situations in which the lifetime is very long. Okay, so, and let's say, as you saw, what I show you so far, just to recap, is that in a geometry, three-dimensional, in which the dipolar interaction is mainly attractive and the contact is repulsive, the system is not collapsing because of the Li-Yang, and the system is stable despite attraction. So then the second step for us was let's rotate the dipole. You see from here, I just changed the direction of the magnetic field. That's trivial in the experiment. And I do this type of situation here. And now I have both interaction which are repulsive. So the dipole-dipole interaction is mainly repulsive because it's much more likely to get atom in this direction in average. And so then what we thought is, okay, well, now I have two interactions, both are repulsive. The system before, also with attraction, was stable, should be really stable, nothing would happen. And here comes the second puzzle that we got. And so at the beginning, when the contact interaction was, repulsive and big, we see the nice Bose-Einstein condensate. So here I'm showing you in the momentum space. Okay, so this is the momentum distribution of a Bose-Einstein condensate, which have the majority of atoms at k equals 0, that's the condensate. But then, of course, you have a little bit of spreading due to the interaction and quantum depletion and all these things. And so in real experiment, you don't have only the k equals 0. But then we thought, let's decrease a little bit the contact interaction. Still everything is repulsive. And what we saw, and this was really shocking in our experiment, we saw the appearance of another type of momentum distribution. You see, it's very different. You have a central peak and two side peaks that are exactly at the same distance from 0. We thought for many, many months that this was a mistake of the experiment, that we had maybe reflection of light, that something was wrong. But actually, this was really physics. And it took us a while to be convinced. And actually, the line of thinking is the same. If we have now in the momentum distribution two peaks at some specific special k, let's say, then this means that the Fourier transform is something which is modulated in space. Okay, that's simply the Fourier transform. So that means the lambda of the modulation should be 2 pi divided k, special k, and this is a k. And then we wanted to understand what was generating this spontaneously. I'm not imposing, it's a gas, I'm not imposing any modulation. It's coming by itself. It's a gas that by itself creates a very regular periodic modulation. We also observed this not only momentum space. Later, we developed a new imaging technique, and you really see in real space, this is a Bose-Einstein condensate where it's very light, is a lot of density corresponding to a peak of our Thomas Fermi profile, if you want. But then we really see this modulation also by eyes, the gas that start to become spontaneously modulated. And so our first idea that was right and wrong at the same time was, this is a paper that was put in the archive in 2017. The referee thought it was trivial or was only mean field, so he didn't want to publish us. But this, I think, it's one of the most important results of the whole talk that I will present. So our understanding at the beginning was, maybe we have a ground state which is quiet, and then there is somehow some excitation. Then I have to look in the excitation spectrum of the ground state, which have a special k, and then when the real wave function is modulated. This was our understanding. So it's let's say, a periodic modulation on top of a ground state. And so then we were trying to search for this special K. If this is the picture, in the spectrum of excitation, you should have some special K. But actually, unfortunately, in the weak interacting Bose-Einstein condensate, the Bogoliubov spectrum of excitation doesn't have any special K, because you see here that's a linear phonon, and then it's simply quadratic flip particle. But it was a very relevant paper many years before, almost 20 years before our experiment, that showed that if you also have dipolar interaction, the spectrum of excitation gets strongly modified. And it has, let's say, a minimum of energy at a special value of K. This is resembling to the physics of superfluid helium, so this historical, let's say, textbook image of superfluid helium with this Roton minimum. And actually, we went to do another set of experiments hunting for this Roton minimum. And we observed, so we developed a very novel technique to be able to measure fully, so in a very large range of K of momentum, the spectrum of excitation of a dipolar BC. And if you see, this is really developing this Roton minimum. However, as you can see here, there is still an energy gap, so the system is still a normal BC, and then eventually the spectrum, if you're able to excite, you will give this energy. But then the question happens is, what happens if this Roton minimum soft completely? then you don't need any energy cost to create this excitation. And we thought that our original 2017 paper was exactly probing this physics, the full softening of the Roton. So for some reason of interaction, the Roton would soften, the system enter in the Roton instability, and then create all this modulation and excitation. So our understanding of what we were observing was this Roton instability. But there was a problem that we didn't, fully discuss in the paper, just in the conclusion, because actually, if you have a Roton instability, then the modulation should exponentially increase, while we saw the system stable back at that time. So what does it mean? It means that we saw that so this is kind of the size of the density modulation. So at the beginning, normal BC, so the normal BC, no contrast, no modulation. Then the modulation was exponentially increasing, and now a Roton instability, according to Bogolyubov theory, would become imaginary excitation that would always diverge. While we saw that at some point, it became stationary. Okay? And so something else, something more is happening besides simply this excitation. And there was a very relevant paper, theory paper, done about our original result that was actually, let's say, suggesting that at this point, due to the Lee-Wang-Yang interaction, the system would not undergo, let's say, imaginary excitation, but would stabilize due to the Lee-Wang-Yang and drive the system into a new phase transition, into a new ground state. And this new ground state, in similarity with research in condensed matter physics, was a supersolid ground state. So this was really the key paper that put in contact our observation with the possibility to have created a new phase of matter. And indeed, later, this was a much more dedicated experiment. So we prepared the normal BC, we tuned very finely the interaction, we and start to see this density modulation appearing and studying. And this type of studying then later was also done in the group of Tillman Fau in Stuttgart and in the group of Giovanni Modugno in Pisa. And also, again, we repeated the same experiment as the 2070, but more dedicated, more perfect, more clean, and so on, with new also observation. And the system actually could also be made extraordinarily stable in our experiment, because we find the right isotope, let's put it in this way. And so to recap everything what I said so far is the following. Take the gross Pitayevsky without the Lee-Wang-Yang interaction. So the effect of the dipole-dipole interaction is to change a little bit the ground state of a BC and to change tremendously the spectrum of excitation by making emerging a Roton minimum. Then change a little bit the parameter, make the dipolar interaction more important, the Roton will soften, and here the system will develop a sort of modulation. The gross Pitayevsky in this form cannot describe anymore the physical observation and cannot observe this because it will always predict a collapse. That's why you need to introduce quantum fluctuation in the form of this extended Lee-Wang-Yang interaction. And then from this you get really that the quantum fluctuation stabilize a supersolid phase of matter. We studied many properties. I don't have the time, so we could study the phase coherence. That's let's say the phase is a global observable, but you can measure difference of phase. And so we could study how the modulation is appearing, how the phase is appearing. And it's very interesting. This is a spontaneous symmetry breaking. Both the phase is a spontaneous symmetry breaking, is a U2 spontaneous symmetry breaking, and the modulation is also spontaneous symmetry breaking. You might ask which of the two break before, if you enter in a supersolid state. And we studied all these properties. We also were able, from a thermal gas, without having to enter the supersolid by changing the interaction, just by cooling down, to directly supersolidify. This is something special. We are the only one able to do this. And so really you see now this is from a thermal gas. You maybe recognize this type of picture of a BC, but the difference here is that you have this side peak. And here you can see in real space, just by decreasing temperature, you get the supersolid state. And also, the next step for us in our experiment was to say, okay, here we have a state that breaks translational symmetry only in one direction. So you saw it's a string of peak. So you have, let's say, but what happened? I want to make it bigger. I want to scale up. I want to have as little, let's say, finite size effect. And for us, it was possible to develop a special technique that allows us to go from this ground state to a ground state in which you see here you have two droplets, two density peak, to go in a configuration which is a zigzag configuration. Now here you start to acquire more two-dimensional character. We can make it even bigger, the two-dimensional character. And what was really important for us is that we could put really a circular supersolid state in which the density peak are organized in an hexagonal lattice. Why was so important for us to have the cylindrical symmetry? Well, it's always in 3 dimensions. It's just now. What does you mean? Lattice of what? So these are, yes, so you have, so here, this one, so you have a 3-dimensional object in which you have, let's say, all these, you will see later in some simulation, you have this kind of droplet, but you are measuring from one side, so it's like projection in 2 dimensions. Yeah, I'm not slicing, I'm just, the imaging, it's done in this direction. So it's, this is the 2-dimension, is into and the other no. I think you cannot have a 3D supersolid with dipolar interaction. But this was very relevant for us. I don't know how I am with the time. I think bad. No? Oh, incredible. I just gone. Okay, so fine. Now, because I really want to tell you that when you have cylindrical symmetry, this is really an ideal geometry to create vortices. You want to have 1 hour anyway. Okay. So, and then what we wanted to do, this is a 3-dimensional gas, we wanted to learn how to rotate now this gas. This was the really next level of complexity in the experiment, how to rotate this gas very precisely without destroying this very fragile supersolid phase, okay? And so, and why we wanted to rotate it? Because we want to prove that the supersolid state can host quantized vortices. This would be really the ultimate, if you want, proof of the dual superfluid and solid, let's say, type of properties. And so, of course, you know why, let's say, vortices are very interesting. I don't have to tell you, we also heard very nice talk today about vortices. I mean, in a classical fluid, you can really steer your liquid and maybe you have a big tornado. In the case of Bose-Einstein condensate, if you start to steer, nothing happens because the condensate doesn't want to rotate. I mean, the velocity field is irrotational. That means that the gas would do anything to not rotate. It doesn't want to have, let's say, a macroscopic angular momentum on itself. So at the beginning, is able to, let's say, despite the rotation, he's really not rotating with the container. But then if you increase too much the rotation frequency, the system is not anymore able to ignore your rotation. And so the strategy would be, instead of build up a giant angular momentum, is to create a lot of quantized vortices into the system, like here. And there is a special critical frequency above which the vortices appear. That is known and has been very well observed in many experiments, superfluid helium, in bosonic condensate, in strongly interacting condensate. All this hole that you see is a vortex. and also an exciton polaron, and also in superconductor. Now, but the question was for us how we rotate this new state of matter. I cannot simply rotate everything, it's so dependent on the trap. Every mismatch will destroy it. And we got an idea from classical physics. What you see here, I did it at home for my kids at the same experiment. So you can buy an object, a classical thing, which is called ferrofluid. So it's like a water or a suspension, and then you have inside a little powder of metallic magnetic particle. Then you put everything together, you have a supersolid. Now this supersolid, if you have the rotation, if a magnetic field is rotating, the ferrofluid, that's a classical system, the ferrofluid rotates with the magnetic field. We wanted to do this in our quantum state. Okay, and so this is what we did. Now what you see is simulation, because likely, we also have let's say a theory group in my group, and so we could really develop the, let's say, theoretical understanding, which is crucial in this complex system. So this is the simulation of the ground state of a non-dipolar gas for our parameter. If we add on a dipolar interaction, because there is this tendency to align to favor attraction, you see that it's getting, let's say you have the phenomenon of magnetostriction, but now if you rotate the magnetic field, all the gas is following. And so if you start to rotate the magnetic field and spin, what you get is this type of, you can really rotate just by changing the magnetic field, you can rotate your gas. And this is what we did. And here you see the real-time simulation of, let's say, the magnetosteering of a supersolid, in which you see this is for a small ground state of only 4 density peak. And you can rotate. And this was now, and you can very well control the frequency of rotation. So you can go above any critical frequency and ask yourself if you have vortices. And here now it's the same figure of here, but I'm looking in 2D, no? I'm projecting in 2-dimensional. And so this is now the experiment. So that's in the theory, sorry. That's in the theory when we magnetosphere. I don't know why it's blocking. And this is now the experiment. We were really able to rotate for extremely long time of hundreds of milliseconds our system, hunting for vortices. I don't want to go too much into detail, but every vortices have 2 properties. One is that it's, you don't have any atom, so it's really a hole in the matter. So that you can see here is a density dip, nothing is here inside. And the second property is that you have a 2-pi phase winding. Now, in normal Bose-Einstein condensate, it's very easy to see the density dip because you have to imagine a normal Bose-Einstein condensate is almost constant density, and then you have a hole. While it's very difficult for a normal BC to measure the phase winding, to measure directly the phase. The supersolid is the opposite, actually, because that's the type of density distribution that we have. You already have density maximum and density minimum also without vortices. So it was really difficult for us to observe vortices in the system. But actually what is very interesting is that if you now, so there's really a challenge to see in the density, but actually what happens is that it's very natural. If you make this system to expand, you would have that matter wave interference if you want. And if the system, this is really 3 Gaussian, if you want, with the phase relation. If you make the expansion and you don't have a vortex here, you have really matter at the center. While if you have a vortex, the situation is really different. If the vortex is inside, you have destructive interference of matter and a hole in the middle. And if there is no vortex, you have constructive interference, so matter is in the middle. And so what we studied in our experiment we did this. We rotated the the supersolid phase. We did this expansion measurement, and really for the given expected critical rotation frequency, we saw the vortex as a destructive interference in the middle, and if we rotate slower, we see this type of pattern here. Now, I don't really want to go now too much in the detail because there are a lot of interesting properties of the vortex, but I would like to, let's say, maybe just come to one general consideration to close. Because, I mean, we kind of, with the observation and the creation in lab of this novel phase of matter, you open a new field of research, which is basically modulated superfluidity. What does it happen? Even, let's say, you might be familiar with this Landau criterion of superfluidity. Even this simple criterion breaks down because you have density modulation into your system. So in a way, you are really probably, that's really the right place to ask for help and try to understand what does it mean superfluidity, what does it mean superfluid fraction, what does it mean all this quantity, whether there is a criterion for superfluidity or not. We have to rethink to the basic phenomena of superfluidity and macroscopic quantum coherence, but now adding the spontaneous translation, breaking of the translational symmetry, and understand what is really the impact in this general field that it's actually, by the way, very much increasing of modulated superfluidity. That said, there is already a connection that was very, let's say, surprising to us, that came a little bit out of the box, actually, with discussing in a coffee break. That's why it's so important to go also in conference where you have people from very different fields coming together. And actually, for once we understand the supersolidity in this, let's say, in quantum gases, what can you do with this? What can you learn from this state? And actually, it's turned out and that now we do really a big jump, because it turned out that maybe there is a supersolid phase inside of a neutron star, that there is a connection between this general fundamental phase of strongly correlated particle and what can be inside of neutron star. And I would like to tell you why and what is our touch on this. First of all, let me remind you what is a neutron star. So the neutron stars are typically very small objects. Probably the radius of a neutron star is smaller than Vienna. But despite being a very, very tiny small star, it hosts a gigantic mass. Typical weight of a neutron star is higher than the one of the sun. It's in between 1.2 to 2 solar mass. So it's a very small object with a lot of mass inside. So you can immediately understand that the density inside of a neutron star is really extreme. It's probably one of the most dense objects existing. The temperature of the neutron star, and this is also interesting, is incredibly low for being an astrophysical object. So typical astrophysical objects have a temperature of mega-electron volt. The neutron stars go in the regime of a kilo-electron volt, really by the way they are produced, because, I mean, they kind of have a huge explosion, hot part leave and the coldest part remain. The neutron star, if you now consider to be rotating neutron star, which has scored a pulsar, they are almost perfect radio clock. Because the rotation of the neutron star, the axis of rotation have a tilt with the magnetic axis of the neutron star, because of this angle mismatch, they emit light in an effect which is called the lighthouse effect. So this is really the lighthouse, and we, on the Earth, we kind of measure where the light is pointing to us. It's rotating, it's almost a perfect radio at radio frequency. So a full rotational period is in the order of milliseconds. So an object heavier than the sun, smaller than Vienna, rotating a millisecond and emitting light. It's almost a perfect clock, radio clock. It's used as a radio clock. On the scale, however, is not a super precise radio clock, because on the scale of, let's say, years, the pulsar is slowing down because it's emitting photon. Photon carry energy, so they decrease their energy, and so they decrease the rotational frequency, they slow down. This is called, let's say, the steady stellar spin down of every pulsar. Okay, that's known. And this is understood, it's not just an energetic argument. But, and this is really the interesting part of this story, sometimes, okay, and nobody really knows completely why, sometimes, this is the rotation frequency of the neutron star spin up, and it gets glitches. Sometimes it's increasing. Now, I have magnified enormously this effect, typically these glitches, so it's slow down, and sometimes, and then slow down. These increasing spin up, it's called neutron star glitches. Typically, this jump, delta omega, is extremely tiny, go from 10 to the minus 3, let's say, to 10 to the minus 5 in relative unit, no? So I've just... This depends a little bit on the star, and it can be in the time of days that goes up and then spin down, or even faster. And then this, I mean, there was a lot of theory. I mean, astrophysicists are really fantastic, in my opinion, because, I mean, they really come up with genial idea on how, I mean, a model, a phenomenological model that can explain. And there are many different models actually explaining the glitches. But let's have a look at one of these models that is the following. So one model is the idea that the neutron star have different layers. A core, which is liquid, the density are extremely strong in the center. Everything is liquid. And because of the high density and the low temperature, the core is superfluid. That's why many times we see superfluidity is in the core of a neutron star. The outer part is really a solid, is a crystalline solid crust. And there are theory thinking that between the superfluid and the crystal, in the inner crust, what can it be? Between superfluid and crystal, maybe there is a phase that combines superfluidity and crystalline phase. There are many different theories, but there are fermions, but because of the huge density, these fermions are doing, let's say, a Cooper pair. So it's pretty established. Yeah, well, I mean, we can discuss a difference on superconductivity and superfluidity very longly. But what you have is that, let's say, two fermions. So the idea is that they're in the liquid phase, so it's not a solid, and they form the Cooper pair. So they are kind of this bosonic bound pair made of fermions. And yes, exactly, in the core. And then in the outer crust, crystalline, and then this in-between crust is very much thought that have the two properties inside. But they didn't, now they changed the way they speak about this crust, I mean, which for us is really cool. But before it was called pasta phase, lasagna phase, I mean, a lot of, food-based things. But now they start to use supersolid keywords to really identify this phase. Okay, and so what we have in our lab is something that maybe can mimic only this inner crust. And together with, let's say, Massimo Mannarelli, so which is your colleague, we then run some simulation, which I would like to show you. So that's not experiment, it's only simulation. And the next step will be to observe in the experiment. So let's say we consider a ground state of a supersolid ground state with all this density peak in, let's say, Bordeaux or a dark green. And then the black point that you see are all vortices. So we prepare a ground state in the rotating frame that hosts a number of vortices. And then from this ground state, we start to slow down the rotation. Because we are slowing down the rotation, the number of the ground state is changing, because for having every given rotation frequency, there is a number of stable vortices. If you decrease the rotation frequency, you decrease the number of vortices in the ground state. At some point, these vortices will become unstable and try to escape. So what you see here is the full density with the peak and the vortices. Here, we just highlighted the vortices, and here you see the residual in terms of the position and what happens at the density peak. So now look here, a vortex is escaping, a little glitches is increasing. And then you can slow down, that's the steady stellar slowdown, and again, you have a little glitches appearing. And so it seems that with this system, we can kind of see one of the proposed phenomenology that in the inner crust, when the system is slowing down, at some point the vortices which are trapped in the inner crust start to escape, hit the outer crust, transfer angular momentum in the outer crust, and have this little jump, which then they decay because the vortex evaporates in the atmosphere. And so in this, I think it's really a very nice example of what we can learn from ultra-cold physics to very diverse and the universality of the physics. And as a last comment, as you see here, we don't need not only see the glitches, but also a very short time dynamics inside, which is related to the reorganization of the crystalline pattern once the vortex leaves. And actually, after this work, the astrophysicists went back and they actually do see this type of also fast dynamic in their glitches. So I think that this is, let's say, more an opening for the future and for the beauty of the universality in strongly correlated quantum matter. With this, let me thank the group and all the collaborators that have helped us to understand and to redecode the physics. And with this, I would like to thank you for your attention.